But today we're here to talk about types and types of GBM, what causes them, how they are treated traditionally right now, and some innovations in surgical and adjunct treatments, why they work, and how to access them. And then, of course, we were here to answer all of your questions. Oh.
Okay.
Alex, can you see it?
Yeah, I can see it. You're cutting out there. Did you say something?
No. Hello, hello, testing,
Yeah,
testing.
that works. That's good.
Okay, fortunately, I don't have to talk very much, so that's good.
Yes. Okay, so glioblastoma multiforme, also known as GBMs. They're a type of cancer. They're typically based on a type of cell called an astrocytoma, although not always. There's many variations. They can also be glial cells. But in general, the GBM is referred to as a grade 4 astrocytoma, whereas lower grade brain tumors, grades 1 and 2, are referred to as gliomas. So next slide.
Oh, hang on. There we go.
Slide 3.
Sorry?
Slide 3.
Oh gosh, see, I told ya. It's gonna be fun.
Okay, yeah, sorry. Yeah, slide 4, sorry.
Is that good?
Yeah, no, slide 4 now.
Okay.
Sorry.
Don't mess me up here, Alex. It's hard enough right now. There we go.
Okay.
How's that? Are we happy?
Yes, perfect.
Okay.
Thank you. So there's many other types of gliomas, astrocytomas, anaplastic astrocytomas, oligodendrogliomas, anaplastic oligodendrogliomas. There's a variety of different combinations, and they all refer to the cell of origin that they or the cells that make up the composition of the tumor. Oh. So next slide. Yeah. So low-grade gliomas can turn into a GBM. And that is really a big concern. And so a lot of the efforts in diagnostics is determining, what sort of grade the person has and what is the capacity for that particular person's tumor based on molecular features to turn into a high-grade GBM. So a couple little facts about GBMs. They're more common in men as compared to women. Next slide.
Sorry. Oh.
Okay, so what are the causes of them? So prior therapeutic radiation, chemical exposure, inherited diseases where there's genetic mutations. One of the interesting facts that we're starting to see about GBMs is a decreased susceptibility to an allergy and an impaired immune response can be associated with a higher risk of GBM. And so in other words, there's an inverse relationship between having bad allergies and glioma development. Yes.
Yeah, when I saw that in your notes there, I was quite surprised, actually. Yeah. I actually read it over about 5 times and I thought you had mistyped it. I thought, he's got it wrong. But
cool. Yeah. So it's all based on an allergic response. Our allergy response is based on it's created to fight parasitic infections and blood flukes and so on. And so, one example of that is a common infection, Toxoplasma gondii infection from uncooked meats, that they call it barbecue season disease. That can result in formations of cysts in the brain. And these cysts can act as precursors to GBM. So once again, the big thing with cancer is the allergic inflammation responses. So having an allergic inflammation protects from a wide range of different environmental triggers, xenobiotics, carcinogens, anything that can lead to damage of DNA or DNA mutations that lead to cancer. So allergies and GBM, more on this. So cells that mediate an allergic response regulate inflammation. And this is what causes escape. Cancers can escape immune responses. So the cells responsible for an allergic reaction are referred to as mast cells. And they're found in high numbers in GBM tumors, interestingly enough. So there's definitely an association between an abundance of mast cells and GBM tumors. So, and just to summarize on that, people with allergies who have a strong overactivation of their immune system to allergies or different allergenic substances, pollen and so on, tend to have lower rates of GBM. And people who don't have allergies tend to have higher rates of GBM. It's thought that their lack of an immune response to allergens also results in a higher risk to GBM. So in short, and this is very basic, there's two subtypes of classic GBM. There's what we call primary glioblastomas, and they typically develop around 65 years. They have no precursors, they just come out of nowhere. Secondary glioblastomas develop in younger children. They often stop growing at puberty for some reason. And then, often children have a history of complaining about headaches and problems, vision problems and headaches that tend to go away at around puberty. So definitely, if there's children complaining about migraines and headaches, I think it's a really good idea to get them a MRI scan or some sort of imaging and really look into that. Because often what happens is these tumors will stop around puberty and then they'll start growing again as young adults, in their 20s or 30s. And they typically start out as a low-grade, diffuse astrocytoma or anaplastic astrocytoma, and then they can develop onto a more aggressive form of cancer. Yeah, so next slide.
Sure.
So the important thing about knowing the difference, because often patients will come to us in their 50s or even 60s, and they'll have these glioblastomas, and we'll want to know if it's secondary or primary. And it's very important because they have very different molecular features to them. So primary GBMs often show something called EGFR overexpression. It's a type of overexpression of a mutated EGFR. They often have deletions in a gene called PTEN, which results in overactivation of the PIK-AKT signaling pathway. They have something else called CDKN2A, P16 deletions. And less frequently, they have something called MDM2 amplification. Whereas secondary GBMs, they kind of have they're very diverse. But one of the things that really defines them is a P53 mutation. And this seems to be one of the early causative mutations. P53 is referred to as the guardian of the genome. It's one of the first real tumor suppressor genes that we ever discovered. And it has a lot of jobs and basically regulates the integrity of the genome. So it's a very important gene. So, it's very important to understand what the mutations you have are. It can really help in determining what sort of treatments will work, and more importantly, what sort of treatments won't work. I think it's important to understand this going forward, because there's many great new genetic tests, and you never know. We've had cases where we found people, children, or not children, but young adults with brain tumors that had what's called a BRAF V600E mutation. And we're able to treat those patients with a drug that's commonly used in melanoma, because that's a common mutation in melanoma. And definitely we got some great benefits from that. So, knowing targeted mutations, you never know what you can have. And it's always important just to know what you have and get the tumor DNA sequencing and see if there's anything that's targetable.
Agreed. Agreed. Makes a huge difference.
Yes. So diagnosis of GBMs, typically, patients complain of headaches, vision loss, sometimes confusion. And then typically the GP, family doctor will order some tests, an MRI, a CT scan. And then if they do find a tumor, hopefully there's an option of getting a biopsy, although typically the biopsy is done post-surgically. So sometimes they don't quite know what type of tumor it is until after the surgery is done, where they get a better idea. Although there's some indications, radiologists are fairly good at looking at different factors and trying to determine, with how the tumor looks, whether it's a low grade or a high grade or, a GBM or not. So standard diagnostics, CT scan is commonly used. And then MRI is a close second. There's many different types of MRIs now. They can use diffusion agents. There's MRIs that are specific for different organs. it's important to look at the different options. Typically, what these tests are done is they're used to show if there's a mass where there shouldn't be, and then they'll do repeat scanning over a period of time, called serial scanning, to identify it and see if there's any growth, or if it stays the same size or changes shape or grows. It doesn't really say for sure if it's a cancer or not unless it's actually growing. Although there are other ways they can look at, on an MRI and a CT scan to determine whether it's likely a cancer or not. But once again, it's a mass. And one of the biggest problems we do have right now in GBMs is that it's really tough to tell, is that a metastasis? Is it a brain tumor, or is it just a benign lump? And, it's something that is a bit of a problem and causes a lot of confusion. So normally we would use a PET CT scan for something like this, but unfortunately, because the brain has a lot of high metabolic activity and it uses glucose, then the standard PET CT is not a reliable indicator. However, we have used PET CT before on certain cases of brain tumors, typically more often or not, to see if the brain tumor is active or not. What they have to do, though, is they have to reset it and get the basic FDG status and SUV status based on just the brain. So it's not a great tool. It can add information, but it's not really used a lot in brain tumors right now.
Yeah, we're so pro PET CT for every other type of cancer, pretty much. And there are some new types of PET CT that are very specific to different types of cancer. Do you think that they will be able to isolate a specific antigen or something?
I do, yeah. I think that's going to happen soon. I think there'll definitely be some sort of molecular-based imaging, in the next few years.
There has to be some way to differentiate, for sure. But for right now, what you're telling us is, from an imaging perspective, MRI is best for the brain. Yeah.
And CT, MRI
and CT.
Yeah.
Okay. All right. Well, we did just kind of talk a little bit about biopsy. That, fundamentally, it is the way to conclusively determine brain cancer or not. Would you say, Alex?
Yes. And unfortunately, it's often done after the fact, where they'll look at the pathology of the actual tumor.
So the surgery's already been done, and now they're looking. Is that what you mean by after the fact?
Yes.
Yeah.
Post-surgery.
Okay. Whereas in other types of cancer, you can take a little biopsy, and then decide what you're dealing with, and if a larger surgical procedure makes more sense, or again, that tissue gets sent for genetic testing, and different types of therapy are administered.
Yes, excuse me. I have a series of sneezes in here
from
my allergies. I get really bad allergies, so it's going to come out any minute. So just excuse me if it does. So the standard treatment for glioblastomas are typically surgery, a craniotomy, a radiation therapy. A craniotomy is where they cut the top of the skull or area of the skull, and then they go in there and they try to cut out the tumor and preserve as much normal brain tissue as possible. There's also radiation therapy. And then there's a drug called temozolomide, also referred to as TMZ. And so about 2005, someone called Stoop came out with what's called the Stoop protocol. And so far, that is still a standard of care to this day. It consists of radiotherapy and concomitant chemotherapy with TMZ. So it's using surgery, radiotherapy, and TMZ together. So the treatment efficacy and prognosis. There's a couple of different prognostic features that we look at right now for GBMs, and they're associated with either higher grade or lower grade, although even a high grade GBM can have some of these, and a low grade can miss them. Anything's possible with cancer. We see all kinds of different things, but in general, the lower grades have what we call beneficial based alterations. So one of them is a complete IP19Q co-deletion. And so these are two different chromosomes. So you have the 1P arm of one chromosome and the 19q arm of the 19th chromosome. And both of these arms are deleted in certain types of GBMs. You also have something called MGMT promoter methylation. And there's also something else called IDH1 mutations. So the 1p19q co-deletion that involves a complete deletion of the short arm of the chromosome 1 alongside the deletion of the long arm of chromosome 19. And so those are referred to as P and Q arms. They're typically found in low-grade gliomas like oligodendrogliomas. And then most, but not always, most patients that have a 1p19q co-deletion have mutations in the IDH1 gene, the R132 or the or IDH2 R172. But there's also a huge variation in the different mutations that can occur. So typically patients with grades 2 and grades 3 gliomas with IDH mutations and 1p19q co-deletions. So though, grade 3 would be considered more of a higher grade than grades 1 or 2. But if you have a higher grade, grade 3 with IDH mutation and a 1pq co-deletion, then you have definitely a much better survival time. Typically, it's about 8 years versus 6 years or so in patients with an IDH1 mutation and no 1p19q co-deletion, and about 1.7 years in patients without IDH or 1p9.
So for those at home, wild type means what, Alex?
Wild type means normal versions of the genes.
Okay. So if you didn't have anything wrong with it, that actually works against you in a way.
Exactly, yeah.
Yeah.
So these are beneficial mutations when it comes to prognosis. So another alteration that we look at is called MGMT promoter methylation. And so this can occur in approximately 50% of grade 4 gliomas, GBMs that is. And what it is basically, it's the O6 methylguanine DNA methyltransferase. That's the name of the gene. And so this gene fixes a certain type of DNA mutation called an O6 methylguanine. And this mutation results when an alkyl group, which is basically methylation, is added to the O at the 6th position of the guanine in the DNA. And basically it causes what's known as a bulky adduct. And so it's a big bulky thing. And so when the transcription or translation machinery comes along, it hits this and it's like having a roadblock in the DNA. And so it can't get past it. So the MGMT gene fixes those mutations. However, certain chemotherapy drugs used to treat GBMs, such as temozolomide, are alkylating agents. And what they do is they damage the DNA by adding this methylation group. And one of the things they do is they create this mutation in the DNA so the cells can't copy themselves and they can't transcribe the genes. So that's having a methylated promoter MGMT is definitely a beneficial thing. And it helps us determine whether TMZ is going to work or not. Next slide. So basically a little bit of genetics. A promoter is part of the gene that decides if the gene is turned on or off. So you have a gene and you'll have the start of the gene here. And then before the start of the gene, you'll have something called the promoter. And then on the other side, you'll have the actual gene with its exons and introns. So the promoter region basically is where all the DNA machinery binds, or the transcription machinery binds. It binds it, it opens up the DNA there, separates the two strands, and then does whatever it is, either copying or transcribing into RNA, whatever process we're looking at. So the promoter region is kind of like the on-off switch. So I like to think of it as a light switch. When you turn the switch upwards, it turns the light on. When you turn the switch down, it switches it off. However, what happens is methylation occurs at something called CPG islands on the promoter. They're basically little repeat sections of DNA. And what happens is they have this methylation tag on top of them. So when the transcriptional machinery comes to turn the gene on, that methyl tag is there and it interrupts it and causes something called steric hindrance, and it prevents the transcription machinery from accessing the DNA. Promoter methylation is an important process there is a gene that controls that. There's a few different genes that control that, and they are responsible for making sure that the genes are supposed to be turned off are turned off by adding these methylation tags, and the genes that are supposed to be turned on don't have these methylation tags. And so this is constantly maintained throughout your life. In fact, there is a type of cancer, GBM, that is very difficult to treat, that has damage in the gene that adds the methylation tags to the other genes. So in that gene, we get what's called global dysregulation of methylation. In this case, it's just the one gene we're looking at. So the promoter is a part of the gene that decides if the gene is turned on or off. It's like the light switch. When a promoter region has methylation, the gene is turned off. It's locked in the off position. When it loses that methylation, it can then be turned on. So basically, the MGMT gene has a promoter methylation. It is turned off and cannot fix the damage of the tumor DNA created by temozolomide. So temozolomide creates the methylation to damage the genes, and MGMT fixes it. If MGMT is turned off by promoter methylation, it can't fix the damage caused by TMZ in the cancer cells. The cancer cells can't fix themselves, and therefore they die. So methylation of MGM promoter has emerged as a strong prognostic factor in the treatment of GBMs, and is associated with improved response to TMZ and definitely a longer overall survival rate.
And how do we test for that?
You know, that's an excellent question. I didn't want to get into that because there's a lot of issues with testing. There's many different ways of testing it. We don't really have a great consensus on what is enough methylation to turn the gene off and enough to turn it on, although there are definite standards that we use. But, you know, it's like everything in science and medicine is, you know, you can use it as a guide a lot of the cases, but it's never perfect.
Okay, it's working on perfection right now. Yes, exactly. Okay, all right.
IDH1 mutations. Now, this is a really interesting gene. So one of its important functions is to produce an important energy molecule called NADPH. I won't get into the function of that, but what happens when you get IDH1 mutations, they occur very early on in the progression of the disease. So they start quite early. And what it does is it causes it to produce a different enzyme. The enzyme is called 2-hydroxyglutarate. And this is referred to as an oncometabolite. In other words, it's an altered enzyme that actually causes cancer. And I won't get into how it causes cancer because that's incredibly diverse. We don't know of all of the different ways that it does cause cancer. We do know that having mutations is a cause of gliomas, in having mutations in the IDH1 gene, and there's specific mutations that we look at, but it causes this oncometabolite. And additionally, the cell is no longer able to produce the important NADPH. And that's important because NADPH decreases glioma cell survival by inducing the NADPH oxidase-dependent increase in oxidative stress and by PARP. It's another gene of PARP activation. So not having that NADPH, so this is a double whammy. It's actually a triple whammy. So IDH1 mutations, number one, they cause this oncometabolite that wouldn't normally be there. They reduce the NADPH, and so that effectively allows the glioma cells to grow. And then additionally, IDH mutations also drive increased methylation in glioma. So that's an interesting dichotomy because there is some evidence to suggest that this mutation also causes, while it causes the cancer to occur, it also makes it more treatable in that it causes methylation of genes like MGMT. So it's kind of got a dual function.
Interesting.
So it causes cancer initially, but it's also a positive diagnostic factor. Next slide.
Interesting. It's never easy, is it? This cancer thing?
No, it's not. No. So, you know, what is personalized oncogenomics? Well, we like to think of it as the right drug for the right patient at the right time. You know, it really is the evolution of cancer care. We've been designing new cancer treating drugs based on what we call defined mechanisms for about 20 years now. Ever since the dawn of the Human Genome Project, we've been able to start on targeted therapies, and we've really been able to develop some great new technologies. So precision oncology, is basically uses the most advanced technologies, diagnostics, treatments towards the development of a unique treatment plan for each individual patient. That's the goal of it. Mm-hmm. Next slide. So a little about 4 pillars, the way we look at it. So the 4 pillars are genetic and molecular testing, personalized research. In other words, what is available today? What new data is available as of today? Because that can change daily and weekly and monthly and yearly. It's really important to understand there's 250, 300 different cancer conferences every year. Some of those conferences, like ASCO, can have up to 7,000 or 8,000 different presentations, or not presentations, but abstracts. So, you may go to ASCO and see 5 or 6 different presentations, but if you go look at the scheduling and so on, you'll see that there's actually a massive amount of abstracts submitted. And so there's a lot of information coming at us very fast, and making heads or tails of it is quite difficult. So the other thing is the personalized treatment plan. And that requires having the molecular and genetic features of the patient, and then precision treatment monitoring. What is the best way to monitor? Personally, I like to look at a diverse set of monitoring tools. I like to look at liquid biopsy when that's possible, although it's not really that usable in brain tumors, because a lot of the DNA that gets released from liquid biopsies does not reach the circulatory system. It's stopped by the blood-brain barrier. But there are other ways of monitoring. So let's get on to the next slide. So just a bit of a brief summary. Cancer is a disease of the genes in the DNA. The only way to have cancer is if you have some of your genes altered in some way. There's at least 4 different signaling pathways that have to be altered for a cell to transform from a normal cell into a tumor cell. But there are hundreds of thousands of different genes in each signaling pathway. So the unique amount of mutations that can occur is going to be unique for everyone. Every person is going to have a complete set of unique mutations. Additionally, there's a possibility of having 3 or 4 different mutations at one base pair. Some genes can have hundreds of thousands of base pairs, 200, 300,000 base pairs. If you were to take just 150 base pairs, a very small amount of DNA, a small portion of a gene, and determine how many different combinations and mutations could occur, the possible amount, the way you do that is you take the 4 different base pairs and you put them by the power of 150. And if you do that on a calculator, you're going to get a number that is significantly larger than all of the atoms in the known universe. So just in 150 base pairs of a gene, which is a fraction of a gene, and we have 25,000 different genes, you can have a massive number of possible combinations of mutations. Mm-hmm. So, we're nowhere near to figuring out everyone's mutations. Every time we do genetic sequencing, we find unique mutations, and we also find common mutations, mutations that are common to that type of cancer, mutations that are targetable, that there's drugs that target them, and then, of course, a variety of different mutations that are sometimes unique to the person. And if there's no information on a mutation, it's referred to as a variable of unknown significance. Next slide. So standard diagnostics and pathology can't really show you how to identify treatments that will slow or reverse cancer. Molecular testing is really the key there. You need to know what's going on. Doesn't necessarily mean that you're going to have the solutions, but if you don't know what you're doing, you're kind of flying blind. Mm-hmm.
That's the biggest thing, right?
It really is, yes.
Yeah.
It's not a guarantee in any sense of the word, but without that, you don't have a chance, really. It's just guesswork. Mm-hmm.
When let's just clarify, when you say don't have a chance, what you mean is in terms of your oncologist being able to identify like a personalized treatment plan for you, or something that's really going to target your mutations. Of course, you can't do that if you haven't had any sort of genetic or molecular testing.
Well, I like to think of a type of cancer called AML, acute myeloid leukemia. It's been a deadly cancer forever, and we just haven't had any solutions. That survival rate's been very, very low. However, in the past, 4 years or so, there's been almost 14 new targeted therapies approved by the FDA for AML.
Mhm.
However, each one targets a specific molecular feature. So when a doctor is presented with treatment options for AML, very rarely are these patients have these patients had tumor DNA sequencing. So the doctors don't know which one of these 13 drugs to use. And so what they do is they'll use them in succession. They'll say, well, let's try this one, and let's try this one. If this one doesn't work, let's try this one. When we show up with a tumor map and we say, this is what's driving this version of AML, then they could say, oh, okay, I'll use drug number 7 and drug number 9.
Yeah, they can start you right away on the right stuff.
Yeah, and so the technology is jumping ahead. The production of FDA-approved drugs is jumping way ahead of the indicated testing.
Yeah.
And so that's a bit of a problem.
Yeah, if I could just say that in a different way, we have lots and lots of targeted therapies, but very few patients are given the testing they need in order to find out which one they need.
Exactly,
yeah.
Yes.
Yeah, so that's of course where we come in part,
Yes.
is assisting you to access these tests.
Yes.
And then once we get that testing data for you, and we find out a little more about your situation, our team can do the personalized research element. It really is personalized. It's not just for GBM, it's for you and your specific set of genetic and molecular features and all of the other elements that might be along within you, like other conditions you may have had prior to and various other factors.
Yes.
Yeah. And that gets all put into a short report, ideally, for your oncologist. And I say ideally, meaning depending on how many mutations you find, it can be longer, and how many different treatment options there are. With some of these tests, we can come up with between 10 and 20 excellent different treatment options for people, and numerous of our patients have had 50, 100, 200 genes found with some sort of mutation or targetable element. So that's a lot of research to do, but that all goes into a short report for you and for your oncologist so that they can have the help they need in finding out what you need and how to access it. And then we have the personalized treatment plan. We're going to talk very briefly about targeted therapies now, just so you have a pin dropped in what they are. And then we're going to go into talking about some surgical tools and some adjunct treatment options. Alex, go ahead and tell us a bit about this.
Yeah. So targeted therapies, they're basically, what we're discussing. They're designed to target a specific mutation. When administered with a pill or intravenous, they seek out the cells, which are cancer cells that have that unique mutation. So it's a mutation that causes the cell to turn from a normal cell into a cancerous cell. And the theory of this is to target only the cells that have that mutation that are cancer cells and to leave the healthy cells alone. And so in short, they're supposed to have less side effects compared to standard care, and better results, longer overall survival. And they work by seeking out those mutated proteins or genes or overexpressed genes that are unique to cancer cells and inhibit them. And there's also immune therapy, but we won't get into that right now.
Oh, well, that's the next slide. I snuck in there.
Okay, then.
But I do just, if we think about, standard care being, often a chemotherapy kind of radiation combo, and we think about chemotherapy as a treatment that really kills all rapidly reproducing cells and doesn't differentiate between those that have a cancer-related mutation and those that are just fine. That's why a targeted therapy is so incredibly effective, is because it is addressing the part of the cell that has the cancer, leaving healthy tissues alone. So patients get a better treatment outcome with fewer side effects. That's how that works. do you want to say a thing or two about immunotherapy, Alex?
Well, I don't think immunotherapy really has a lot of role right now in what we're talking
No?
about.
Okay.
So,
All
yeah,
right.
we'll
Well, that
skip
slide
for
is in your, if you want to learn a bit more, you guys can scroll through your PDF that's there. We were talking about off-label a little earlier, weren't we, Alex? You were talking about that drug that was designed for melanoma, did you
Yeah.
say?
Yes, exactly. Yeah.
But because of genetic testing, we can see that certain patients have that mutation for which that drug was designed.
Yeah.
And that is how we support your oncologist to get access to that drug that you really need for you, even if it was, say, designed for melanoma as opposed to GBM or brain tumors. So the genetics really help your doctor to have more options for you.
Yes.
And to think kind of outside of the box of just GBM standard therapy and into, hey, what drugs have been designed for the mutations that this patient has?
Exactly. Yes. Yes.
And I just like to add a little bit about clinical trials. Not that really, it's very rare in this day and age when we get folks this type of genetic and molecular testing that they actually need to go into a clinical trial, really, because there are so many excellent treatments. But a lot of folks have this kind of outdated sense about what clinical trials are. There's a sense that they're very hard to get into and or that they have to travel to access them. Right now, as you can see on your screen, there are over 100,000 clinical trials for cancer around the world, and many of them are accessible through your current oncologist, just with some application. But most of these clinical trials do require stratification in the form of some sort of genetics. We need to know that these treatments that the trials are testing for certain mutations or targeted therapies often, or different combinations of treatments. And so you coming to the trial center, knowing your mutations up front makes a big difference to their ability to get you on board right away. And again, you rarely do have to travel in order to access a clinical trial right now. Yeah, anything else you want to add about that, Alex?
No, not at this point.
All right. You see on your screen, I've got a little note there about Heal Mary. A wonderful group of people, Canadian-based, who have created a lovely, very easy way for you to find out what clinical trials are available for you. It takes about 15 minutes total to find out what's out there and fill in all the application forms, and they can help you. You can do on your own, and I recommend you explore that if you're even just a little curious about what might be possible. But I do want to just say there are so many options before most people ever really need to think about clinical trials right now.
So the focus of today, we're going to split this. We're going to split this into two different parts because there's just so much information on GBMs right now. We're going to focus on surgical interventions and increasing the benefits from standard care. So there are many new treatment options for patients with brain tumors and GBM, but we're focusing just on these. These treatment options are typically off-label for the most part, although a lot of them are done in clinical trials. Some of them are FDA approved, some new ones like gamma tiles. There's lots of different things going on, but right now we're just going to focus on the two most important aspects, and that's surgical excision and doing what you can with standard care. So today we'll be focusing on advances in surgery and advances in treatments. And then the next series on GBM, GBM number 2, we'll be focusing on molecular targeting and advanced technologies. So advances in surgery for GBM and brain tumors. There's two different approaches that have been really focused on in the last 10 years. One of them is referred to as laser interstitial thermal therapy, also known as LIT technology. And basically what it is it's a laser beam from a microfiber thread tool. They put a small hole in your head and they thread this tool to the site of the tumor, and they use a laser beam to kill it from inside. And so it's basically a thermal ablation technique using laser beams. The other one, which is really fascinating, is referred to as corridor surgery, but it goes much deeper than that. So advances of surgery with LIT, laser-based approaches. So typically they use an MRI to guide a fiber optics laser probe into the tumor. And then the laser uses heat to thermally ablate the tumor from within. So it's good for hard to reach tumors. And obviously it's minimally invasive. You're not cutting, it's not like a craniotomy where you're cutting, a big chunk of the brain open out and removing tissue and affecting people. You're basically threading this little fiber through the tissue to the site of the tumor. So it's a great idea and a good concept. However, it has many disadvantages. Number one is it uses heat. So it cannot be used near delicate structures such as nerve bundles or blood vessels. And that's a serious issue because tumors often wrap around nerve bundles and blood vessels. It does not remove the tumor. This is a real problem for a variety of different reasons, is if it doesn't kill all of the cells 100%, some of those tumor cells can grow back. So obviously it's not going to, because nothing's 100%. And so it's going to leave some live tumor cells in there. And then also it leaves the tumor microenvironment in. The microenvironment is an area that there's a chemical gradient where a bunch of different cells live, and there's a biochemical gradient that can actually convert normal cells into either tumor promoting cells or tumor cells themselves. So very important to remove the tumor microenvironment when you remove, when you treat something. So thermal ablation just does not do that. And so more importantly, because it doesn't remove the tumor and it kills it, you don't get any DNA or RNA for molecular analysis of the tumor. And therefore you can't ever do any targeted therapies using this approach. Mm. Excuse me. Oh. As a consequence, LIT therapy has died off. It's being used in other sort of brain operations, such as strokes and things like that. But it's just not valuable in tumors and cancer.
But the whole experience of its rise and fall was, really just over a few years, wasn't it?
Yes, it was. And interestingly enough, the clinical trial, we saw all this coming when it was going on, and I was right against the laser surgery. Lots of companies invested in it, lots of hospitals invested in it, thinking it would be a good tool for GBM, but clearly they weren't thinking about the big picture and the importance of where precision oncology was going. Mm-hmm. And as a consequence, the studies that actually used laser-based surgery found that it basically didn't improve much the overall survival of GBM, and patients treated with laser-based surgeries typically had the same sort of survival rates and recurrence rates as people that had craniotomies.
Yeah, and hence we're so excited about NICO.
Yes, always
been. It ticks all the boxes that weren't ticked by LIT and then some,
exactly.
Doesn't it? So tell us all about it.
Yeah, so NICO Myriad, amazing tool. NICO was a child that died of a brain tumor. And so this company was based on that. The NICO Myriad is, it's like an adaptation of an electric toothbrush, but it's a really amazing technology and tool. And this company has really just knocked it out of the park as far as I'm concerned. I think this is really one of the most innovative precision oncology surgical-based companies out there. Mm-hmm. So basically what they do is they use a pre-surgery MRI to map the brain, and they identify where all the sulci are and try to map a corridor to, create a corridor to the tumor. And then they use this novel tool called the NICO Myriad tool. It has a flexible internalized cutting head. So in other words, when I say internalized, it's got this tube like a straw, and the cutting head has a little cut on the side of it. So it's like a straw, a little cut on the side of it, and the cutting head never leaves the tube. The tube just stays in that tube, and it moves up and down like that. And it's a hollow cutting head, so it can suck out the tumor at the same time. So this cutting head moves up and down. They put the port of the opening close to the tumor, and it basically cuts it. And so because of that, it has some amazing capabilities. So it's also minimally invasive. Mm. And so what sulci are the convoluted folds that increase the surface area of the brain. This is something that has been used, throughout evolution to increase the potential of the brain and how it's used. So the more surface area you can pack in there, the better the brain is going to be able to function. And so basically, as you can see, these sulci are basically just the hollow little folds there. And so when you follow the sulci, you're not cutting directly through tissue. And everyone's sulci are somewhat unique. So what they do is they map out the sulci and they say, okay, this tumor, well, I'm not saying the sulci is unique. I'm saying that the position of the tumor is unique in relation to the sulci. So you may have a tumor that's, right near convoluted fold, and therefore you don't need to go to another side of the brain and cut through tissue. You can just follow this little hollow space and perform your surgery through that hollow space and reduce the need for removing tissue. So the tool provides a flexible tool with an internalized cutting head, as I explained. And then it works inside another tool called the brain path. And so this internalized cutting tool allows the nicomyriad to remove tumors next to delicate structures such as nerve bundles and blood vessels without harming them, because it doesn't use heat. It doesn't use that laser beam or thermal ablation to cut the tumor out. And so that's really important because it allows it to go into areas of the brain that no other surgical tool can do. It can go deep into the brain. They can remove tumors, and more importantly, they can move more of the tumor than any other form of surgery. And it's particularly good for deep-seated tumors that are hard to get to. It also has a nice little light that attaches to the tool. And so you can better visualize the tumor without the need for external lighting, which is not that useful when you're doing surgery through a tiny little dime-sized corridor anyways. You definitely need to have an internal light. More importantly, it removes and stores the tumoral sample so you can preserve it for molecular analysis. It also allows the surgeon to access parts of the brain not accessible via standard craniotomy. And it also reduces damage to normal brain tissues and removes the tumor. So it ticks all the boxes as far as I'm concerned. And here's the tool. As you can see, it looks like a modified toothbrush. The individual that invented that is a real genius in my mind. I had the pleasure of meeting him and talking with him, Joe. And the guy's just a creative genius, in my opinion. I attended a training session for nicomyriad brain surgeons many years ago. I think it's 10, 11 years ago or so in Ottawa. And I sat in the back of the room with, this room full of advanced neurosurgeons from all over the world that were getting their training in this new surgical technique. And all I heard was oohs and ahs at every point of the surgery. And so they did some surgeries, some live surgeries. And, I remember I was sitting next to this surgeon from, I think it was New Orleans or so. And he was kind of guiding me through. He says, oh, that's the so-and-so, so-and-so. He'll never get past that. You can't get past that. And then the surgeon who was doing the presentation said, and with the new surgical tool, we just simply slide that out of the way. And he says, oh, wow, I didn't know that was possible. So this tool allows complete access. So if you look at the nicomyriad, if you look at the very tip of it, you can see the little internalized cutting head there. And you can see it, the cutting tool doesn't extend outside of that. And so it's able to suck up and cut that tumor without actually creating any damage to normal tissue.
Wow.
Yeah.
And did we say yet, like, this goes nostril? Oh, are you there?
Yes.
Yeah.
Traditionally, they have done that. They've gone directly through the nostril. I know that they've done that. And I think basically what they're going to do in most parts is is find the closest access point and then go straight through that.
I see.
Yeah. So once again, here's the Myriad brain path tool. So originally they developed the nicomyriad tool, and then they invented the brain path tool. And so it's made out of a special material. It's a really highly polished, it's a tube, and the nicomyriad tool operates inside of it. And so it's a really highly polished surface that's very, very smooth. And therefore, what they're able to do is they're able to just simply slide these tissues, these nerve fibers and blood vessels that normally would create a barrier to surgical tools. They're able to just slide them out of the way and just move them to the side. And it basically uses a 13.5 millimeter there's different size tubes that they use. And so, for an example, the 13.5 millimeter brain path tool creates an opening of about the size of a dime.
Hmm. Hmm. Quite a difference from opening up the whole brain.
Yeah, and so this is what it is. This is a brain path tool. And as you can see, the tube going into it by the finger is similar to the Myriad tool itself. So the Myriad tool operates within this tool. This tool is able to create a corridor to the tumor from the outside of the brain. And so therefore, nothing else gets in the way.
Got it.
Yeah, so amazing technology. This is how it works, is they plunge, they find, as you can see, that's the sulcus right there. They found the sulcus that's closest to the tumor. And then what they've done is they push the tool through the sulcus and then into the brain where the tool is. And then they're able to stick the Myriad tool in there and suck out the tumor.
Wow.
Amazing technology. So here's conventional surgery. As you can see, the pathway to the tumor in the circle, you can see all of that damaged tissue. And there's another slide to the right, the image to go back.
Oh, sorry. Hang on a second. I'm working on it.
Back. Yeah.
You said other slides. So.
Yes, other position. See,
okay,
there's two brain shots there. So the one is from the top, the other is from the front or the back. I'm not sure if that's the front or back. I think it's from the back. As you can see, look at all of that white damaged tissue and the big hole at the entrance point where the cranium was, the skull. And you can see that's a lot of damaged tissue just to suck out that tumor. So go to the next slide. Okay. And as you can see, this is from the Nico brain path. And you can see there's almost no damage whatsoever. There's almost no damage to the brain.
I recall you saying the folks that you watched have the surgery that day got up and went home.
They have to stay overnight for.
Oh, was it overnight?
Yeah, well, they're awake during the surgical procedure. It doesn't take very long, but they like to keep them overnight just to make sure that the tumor doesn't start, doesn't start bleeding into the brain and so on. So they do need to be observed. In theory, they could leave that day if everything was good, but they like to be observed overnight at least, just to make sure there's no bleeding into the brain. But
then they're off. The recovery time is so much less.
Yeah, minimal compared to a craniotomy. Yeah. So, yeah.
This is me. I had to have this slide here that, this was over 10 years ago or so that you went to that training.
Yeah.
They've had one of these in Ottawa since about then, right? When
it started, yeah. That's where I went for the training anyways.
And we've been helping our patients access Nico surgeries around the world, but predominantly Canada and US for over 10 years. Yeah. And it's still just not happening, even with all of this evidence to support how much more beneficial it is. So mostly, I think we just really wanted you folks to know this tool exists. And if you are recently diagnosed or surgery is on the table for you, you can access this tool. You do not have to have the full craniotomy, which has all sorts of extra recovery times and downsides and all the things we've talked about, and the potential for unnecessary damage and disabilities. So I guess we really wanted you guys to have this in your brain. Myriad Brain Path. Myriad Brain Path. Just try to remember that one. Write it down. Make a note. If surgery for your GBM or brain tumors is ever recommended, make sure that you find out how to get this for you.
Yes, exactly.
Yeah, and just understand that you're a standard care oncologist, your public healthcare or medical oncologist may not have heard of this tool for the very reason Alex was talking about earlier, with the thousands and thousands and thousands of new studies coming out every year. And most medical oncologists really kind of limit their focus and their own self-education to things that they know that they can immediately access through their cancer clinic.
Exactly.
Yeah, so something to keep in mind. And there's a link here. It's going to be in the PDF that you've got to a video where you can watch the surgery if you're that type of person and you might be interested in doing so. Go ahead and watch. I think you'll be really amazed.
Yeah, so another great development, in my humble opinion, is something called tumor fighting fields. And these are basically electrical fields that attack tumors, and specific GBMs. They disrupt division of cancer cells and stop tumor growth. They don't affect healthy cells uniquely. For glioma cells, glioma tumors, the frequency range seems to be confined between 100 and 300 kilohertz. So I believe every tumor has its own range that is affected by, which is quite interesting. We'll get into that in the next few slides. So how do tumor fighting fields kill cancer cells? Excuse me. One of the things, there's a variety of different pathways, but one of the ways they affect it is through something called mitochondria. So mitochondria are basically the powerhouse of our cells. They create and generate biological energy. They, excuse me, the way they do that is they use a mechanism called aerobic respiration, and they regenerate the cell's biomolecules that are the source of energy. So the source of energy in our bodies is something called adenosine triphosphate, ATP. The way it produces energy is it gives away the P. So it ends up in being adenosine diphosphate, and then ADP can then give away another one of its P's, and it's AMP, adenosine monophosphate. So we don't create this molecule. We get this molecule, all organic, all animal species get this molecule from plants. Plants are the only ones that can create ATP. But what we do is we use ATP and we recharge our cells. We use it to charge our cells. So basically what happens is a mitochondria will take the AMP that's been used up and turn it back into ATP. Our cells then use the ATP to give away the phosphates to create energy, because when you take away a phosphate group from ATP, it releases energy, and that energy is used to power our lives. Most poisons that affect humans or animals affect ATP regeneration. So they'll prevent you from recharging your ATP. So once again, ATP is only produced by plants, but when we eat plants, we gain this ATP. And when we eat other animals, we gain the ATP from them. And so this is where we get these molecules from. We can't make it ourselves, but we do use it and we're dependent on it. And the whole concept of aerobic respiration is one of the ways that we use mitochondrial to regenerate ATP. So a source of chemical energy. So tumor fighting fields seem to inhibit mitochondrial respiration. So they do something they promote something called oxidative stress by raising intracellular levels of reactive oxygen species in the mitochondria. So, however, it's mostly in the cancer cells. It's not in the normal cells. So this produces loss of mitochondrial integrity in the cancer cells. And it also, another mechanism is it inhibits cell division. So we have these structures that allow the cells to separate their chromosomes and separate their membranes and their biomolecules called microtubules. And so these are very important. They're kind of like the cranes of the cell. They're involved in moving structures around the cells. And so what happens is when you get tumor fighting fields, these microtubules are segregated to one part of the cell based on the electrical flow of these. They're electrically charged molecules, so they get stuck in this part of the cell where they can't be used, and they get put in different orientations where they can't function properly. So this is what one of the devices looks like. It's called the NovoCure Optune tumor fighting fields. It was developed in Israel many years ago, and it's gone through many different modifications, but it's a small battery-like device, and this is what it looks like. It fits under a simple baseball cap, and the wearer just wears it, and then the longer they wear it, the better it works. So I think you're supposed to wear it about 16, 18 hours a day if you can. I think that's kind of important. I think the longer you wear it, the better it looks. So data on it. Data's been back and forth because it's really hard to really, it's really hard to develop things based on statistics. So in short, when it was used in newly diagnosed GBMs, it improved the progression-free survival, and that refers to, that's a median. And so progression-free survival and overall survival are statistics that are used in cancer. And what they refer to is when 50% of the patients taking a drug or on a trial, when their disease comes back, when 50% of the patient's disease comes back, that's called the progression-free survival. And when 50% of the patients in the trial die, that's called the overall survival. So that's a time period. So compared to the standard STOOP protocol that I mentioned was a standard care, when they use this device combined with the STOOP protocol, the progression-free survival was 7.2 months versus 4 months for the STOOP. And the overall survival was 20.5 months versus 15.6 months. Now, some patients lived a lot longer, some didn't do as well. But the 2-year survival is 43% versus 31% for chemo alone. Importantly, the 5-year survival, which is only 5% for chemo, was actually 13% when they used this device. More importantly, people in the study were able to maintain their mental, emotional, and physical well-being for much longer than those on chemotherapy alone. So in other words, their brain function was improved. And that's very important when you're dealing with a brain tumor. Sure,
I would think so.
So for recurrent GBM, this is when the cancer comes back. When the cancer comes back, it's not always that well. Things don't go so well. The recurrence is not a good sign. Importantly, when they compared it against chemo, so the Optune device by itself, without chemo or any other treatment, resulted in a 6.6-month overall survival versus 6 months for chemotherapy alone. And that's important because these patients didn't have the harsh side effects of chemotherapy. So this was compared to chemo, not with chemo. So by itself, it's even better than chemo is. Now, of course, we'll get into this in the next slide, but it also resulted in better quality of life, improved cognitive functioning, better memory and concentration, increased emotional functioning, less tension and less irritability. So chemotherapy has a lot of side effects. This literally doesn't. So, if I was given the choice of 6.6 months with this device compared to 6 months on chemotherapy, I would most definitely choose this because I would have 6.6 months of quality survival versus chemotherapy-based survival, which is not the best. So they've also combined it with different things, and there's a bunch of different trials. I didn't go through everything, but when they combine it for second-line chemotherapy, so the previous slide was that compared to chemotherapy. This slide is compared with chemotherapy. So when they added this plus chemotherapy for second-line recurrence, then it improves the survival by 28% compared to chemotherapy alone. So chemotherapy plus this, when the tumor comes back, improves survival by 28% compared to just chemo. And the survival time was 11.8 months versus 9.2. Another drug, Avastin, that's often used in brain tumors. It's an anti-angiogenesis drug. When they added Optune plus Avastin, it increases survival by 31%. So it was 11.8 versus 9 months. And so that was a different study. And so the control group had lower survival. So I don't know if Avastin is better than standard chemo or not. They'd have to do a side-by-side comparison. That hasn't been done yet. Okay, updated analysis. They use something called the integrated survival model. So as I mentioned, really determining what's better using standard statistics is really difficult in this day and age. And the reason is that it's really hard to get people with the same cancer and with the same molecular features. Everyone with cancer is going to have a different individual prognosis based on the type of mutations they have and their general health. And so when you compare this and you try to get these accurate survival data, you're really playing with statistics, and often you're comparing apples to oranges. It's really, in this day and age, impossible to make those determinations. So there's a lot of new models. So in this particular study, what they did was they used a integrated survival model on the same data that we just went over. And what they showed was that the epidemiological data suggests that a glioma survival prognosis improves with time. So the longer you've had glioma and you're still alive, the better your survival rate is. And so the analysis combined trial and epidemiological data to model lifetime GBM survival. And so when they used this new statistical approach, they found that there's a substantial increase in lifetime survival for GBM patients treated with tumor fighting fields. And that's across the different subgroups. So in other words, what they found overall using this, they found that with tumor fighting fields plus the standard TMZ, the survival was 4.2 years, and with TMZ alone was 2.4 years. So there's the potential of doubling your survival. Importantly, patients alive at 2 years after commencing treatment with tumor fighting fields had a 20.7% probability of surviving 10 years.
That's exciting.
It's very exciting.
Those are much better numbers than 2 months. I mean, I appreciate a month is a month, but I definitely like double the survival rate, and 1 in 5 people
Double
being
survival
10
time.
plus years. And this is without any genetics.
Yes.
Yeah. Wow.
Yeah.
Okay. So I'll just do a little wrap up here,
Yeah.
and then we'll circle back around to Ivo and hear a little bit more about his case and his needs. So what we've discussed so far: cancer is caused by genetic mutations. There are many different targeted therapies, and as you saw, 100,000 clinical trials, thousands of papers coming out every year. So lots new treatments and combination therapies coming out all the time, literally every week. FDA and Health Canada approved options. It's just a matter of finding out which ones are best for you, and that requires the genetic testing in order to do that. But as you saw, even without that extra and what we really feel is a very critical tool for the best outcome for cancer patients, just a modification to how you experience surgery. For starters, that some of the techniques that Alex was talking about don't really give you a good sample for genetic testing, something like the NICO would, and this Optune cap. Those are some excellent statistics, and it's so non-invasive, so simple to use. So highly recommend that for sure. So I wanted to let everybody know about this special program that we have for further education and specifically for self-advocacy. Because probably as you're watching this, some of the questions are, how do I get it? Or how do I get my doctor to get this for me? We're of course here to assist you one-on-one with that. But some folks would prefer to figure this all out themselves, and we really want to support you. We want you as well educated and confident as possible about what's possible for you and how to get it. So we've created this online program that teaches you all about this stuff, about what precision cancer medicine is, how to get oncogenomics for yourself, how to speak to your doctor about these things, and how to make sure you're getting the best treatment. We host 2 live Q&A sessions every week, and the link is there if you'd like to find out more. You can also email me. We'd be happy to have you joining us. And last but not least, if you would like to speak to Alex about a personalized treatment plan or just how to start getting the stuff happening for you, and you'd like our help with that as opposed to learning how to navigate it through your own self-advocacy, you can always just book a one-on-one with Alex, and you will come away with a video of your consultation as well as a written summary of all the recommendations with references you can take to your oncologist. So we're here to help you in whatever way works best for you. Okay. So let's go back. Ivo, I'll get you to unmute yourself. And let's recap what you told us at the start of our chat.
Okay, I'm on mute.
Okay. So how long ago, so you have grade 3 right now, you said.
Yes,
Okay. And how long ago were you diagnosed?
I was diagnosed with that in February, beginning of February, somewhere in around 4 or 5, somewhere there this year.
Okay. So fairly recent.
Yes, very recent. This is my post-surgery time. I'm not receiving any treatments at the moment.
Okay. And you had said when you first were speaking to us that you were reluctant to have radiation, and that was something that your doctor had recommended was radiation. Is that right?
Yes, the Dr. Su in Abbotsford, he's a radiologist. And Dr. Nikolakis, who's mentioned that, but I'm not very eager to go for that treatment.
Understood.
Yeah, I think Dr. Nikolakis is an excellent doctor. I would personally follow his suggestions. Now, what I would also do is I would get your tumor DNA sequenced. I would definitely do that for your type of cancer. You want to know what's going on there. Since you've had surgery, that can be done. You just need to get a sample and you could send it off to a company like Foundation One or Caris. There's a multitude of different companies doing tumor DNA sequencing. We have our own panel. There's a variety of different things, but that's one of the first things I would recommend. I would recommend going with Dr. Nikolakis's recommendation. He's an expert. I believe he's also an eco-trained surgeon too. So, by all means, I would suggest, I do suggest following his advice right now. The tumor DNA sequencing and so on can help you if that doesn't work.
Well, it can also, or instead of, right? Like if you're
well, I think radiation is part of what we do with brain tumors to reduce recurrence.
I see.
Yes.
Go ahead, please, Ivo.
This is what concerned me is actually, yes, it does, like Dr. Su mentioned that I have a 50-50 chances that tumor will reoccur. We know that radiation is not pleasant thing whatsoever for a number of reasons. I'm not expert whatsoever. I just happen to understand few things. But the thing is, it's kind of difficult decision, I believe, is because that tumor was located, as you remember, I mean, is on so-called front lobe, is affecting, I believe is affecting my hearing. I'm having a hearing aid at the moment.
Okay.
It doesn't mean that I lost hearing completely, but I experienced that for a long time. So it not necessarily even that is related directly with the tumor itself, which is out of my head at the moment, but I'm sure there is something left over. So, so you believe that would be the best thing? I mean,
I think it's important to follow his recommendations right now. Yes, I do. Okay. It will reduce recurrence, but I don't think that's all you should do. I think you need to find out what the molecular features of your tumor are. Once we get your DNA, then there's a bunch of wonderful, different approaches we can use. Lots of different ways of analyzing DNA. You may have a targeted mutation. There's a wonderful cure match artificial intelligence program that can analyze DNA and RNA. There's lots of important things that we can get from this.
So would you recommend it? What you just mentioned, the cure
tumor
match?
DNA sequencing, yeah. We can help you. We can help you access that.
Yes, you have to have the sequencing done before you can use a bioinformatics program like CureMatch or OmiCure or some others that we like. Yes, so that's the key. So Alex, just to recap, radiation would be advantageous, but while that's happening, get some testing done on the existing tumor sample
Exactly.
so that so you just know so much more about what's driving your cancer, what treatments are available, and that can help reduce the number of radiation therapy treatments that you need, and certainly help you avoid chemo. What's that?
Potentially. Yeah, we don't, yeah.
Yeah.
I mean, you can't radiate the same spot multiple times. You can only do radiation once.
Yeah,
Well,
so
that-
we'll,
Same spot.
This is what was my next question is what happened if after radiation the tumor reoccur or cancer, and if what treatment is available after?
That's why we would do the tumor DNA sequencing.
Okay, so
to determine
DNA.
that.
yeah.
Okay, so how I get that samples? I mean, I don't have them.
Not a problem. We can get them.
So yeah, so you have
So
to.
they are existing. They are existing
Yeah,
somewhere.
yeah.
Mhm.
Yes, in the public healthcare system in most countries around the world, whenever tissue is taken from a patient's body, it's not thrown out, especially if it's malignant. It is stored in the pathology lab of the hospital where your surgery was conducted, as a rule, and it can be stored for decades. Actually,
Okay.
they keep them for at least a decade. So your tissue will be there. And we can access that. You just need to sign a release form to give us permission to do that. And then we can take care of everything in terms of coordinating your test and getting the data to you and your doctor. But that's the way to have a list of treatments to back up.
I agree.
what you're doing
I'm
right
following.
now.
Yes, I'm following some of your shows or whatever you call that, and yeah, I'm interested into it. Of course, now the cost is obviously another topic to discuss. Is there any possibility to get access into some government-sponsored things, or do I have to pay everything by myself?
Yeah.
Yes, for sadly, this is what we were lamenting about earlier, is that the drugs are available, but the testing required to match you to the drugs you need is not covered by standard care as a rule.
So DNA.
Pardon me, go ahead, Ivo.
Sorry, I interrupted. So DNA will be exclusively on my cost. I mean, the part of the treatment probably is DNA, right? And
yes, if you don't have insurance coverage or critical illness coverage to address those things, then as a rule you are paying out of pocket for the testing, but that allows you then to circle back into the public healthcare system, present your medical oncologist with a more refined diagnosis for you and more options, and those are usually covered.
Yeah,
this is what is my question too. So that BC cancer basically don't go in that far to make a DNA test. They don't have that information.
well, if you're part of the POG program, they do, but they don't always share the information with you or the doctor. So it's best to just do that yourself. Hire a secondary company such as us or Foundation One or Caris or one of the other great companies. Get that information, because you could take that information anywhere you want. If you decide to go down to one of the American hospitals or go to Europe, you take that information with you. That's information on your tumor that you own at that point in time.
Yeah. And
so, but okay, that sort of, to my understanding, if I understand you correctly, so that BC cancer did have done that, but the data is not available to me.
No, I don't think they've
no. Alec, no.
Okay.
There's, let's just back up the bus. In standard care in Canada right now, if your doctor has not asked you to pay for genetics, you probably haven't had any, or if you have, you've had a spot panel that's looked at 5 to 20 maybe commonly associated genes with brain cancers, but not specific to Evo. So we like to recommend a test that looks at 550 genes.
Excuse me.
So your doctor would have to get your permission to sign you up for the POG program. And as like right now, the POG program isn't really taking new people. And that's just for anybody who's watching who hasn't heard of that. If you're not specific to BC cancer, it's not
Sorry, I
right to
lost-
you because you need to be a patient to access POG. Yeah, so that's the sad, frustrating nature of cancer care right now, Evo, is that it is upon the cancer patient to gather some more diagnostic resources in the way that we're talking about right now. But what is exciting is because of what Alex is saying, this data translates around the world. Your mutations are your mutations. They don't change whether you're going to the Mayo Clinic or BC Cancer or to Germany for treatment. So every facility that you might want to have assess you or provide you with service will utilize that information. It is very beneficial. And of course it does, if we're just thinking right here, right now, it helps your BC Cancer medical oncologist to know what other options are beneficial to you, and it allows them to have the information they need to work outside of their standard operating procedure in terms of those treatments that we listed earlier. And that's what matters most, is without this data, they can't in any good conscience prescribe something else for you. With this data, they can. And there are hundreds of targeted therapies that are approved for use by Health Canada, and you can access with coverage.
Okay, can you please give me an idea how much would cost me to get the DNA total?
What I would suggest you do is book an appointment with us, and we can talk about both your case and your wife's case, and we can look into compassionate access processes for you. You know, we can provide you with compassionate access forms, you know, where you can apply to get these tests covered potentially. You know, definitely, I think it's important for you to book an appointment with us and actually have a proper, you know, long discussion.
But I can't tell you, but you're asking a fine question, and I'm going to give you an answer to that specifically. But Alex's point is the main point, which is we need to see your information, and then we could tell you which tests would be best for you, because there are so many different types of genetic tests right now as well. Anywhere, the genetic test itself these days, depending on where you're going and how many genes it's looking at, if you're paying privately, you're looking at about $3,500 to $6,500 Canadian for the test, for one test. And there are a few different ones. So again, depending on which would be most suitable to you. And then additionally, you should be thinking in terms of, okay, if the test is just going to give me raw data, like the test report is just going to tell me these mutations are involved in my cancer, you want to make the best use of that data. So you definitely need to budget for some personalized research. That second pillar we were talking about, so that the things that are going to be most advantageous to you in the way of treatments are presented to your doctor. So the testing and then the research to link you to the right treatment that is accessible in your cancer clinic, that's the combination. And that may or may not include extra bioinformatics programs like the Cure Match and the Omacure and a few other things that you've heard us talk about. It really depends on what the test turns up for you, what's going to be best, and you know, how many options we find and how easy it's going to be to convince your oncologist. Our job is to put together a solid argument, enough evidence that they can have confidence prescribing something else to you. The personalized research, depending on how many mutations your test turns up and where you're having that done, can vary anywhere from about $3,000 to $8,000. Just again, depends on all the mutations. You can, if you're having our team assist you with that, Evo, you can just tell us, this is my limit. We'll do everything we can within your budget to get you all the treatment options that would benefit you. And of course, the advocacy is helpful. You're not an expert in this stuff, and trying to talk to your doctor about it and, you know, and answer any questions or, you know, help them help you. That's extra stress you don't need. So that's part of what we're here for too. And that's what we provide as part of our research and advocacy services.
Definitely, you know, everything I hear today is very helpful.
Yeah.
Far from not. And yeah, I was looking for a number of doctors, even oncologists, to discuss things, but they couldn't really give me any decent information about situation. Not for me or for my wife. It's kind of I understand that we need the DNA to get deeper into our situation, and
Yes. Yeah. Yeah.
I
So
have
for
no
you,
problem to
go
pay
ahead.
for it if it's not any other option, of course.
Yes,
Um,
that's right. So first things first, if we can have your, the way their consultations work is we gather your medical records. Alex and his team will have an overview of some of the most current information there. And then they will meet with you for an hour or so, depending on your case and your needs, and discuss what can be done now in the way of treatment options and additional recommendations. And then if you'd like testing, we know which test is going to be best for you, and then we can give you all the
Okay,
information.
that initial consultation, if I may, how much that will cost?
That's 500
Sorry, I don't hear you.
Yeah, you're
ST. We're
cutting
in
out.
Canada, so that's it's 525 total. What's that?
You're
Sorry.
cutting out.
Oh,
You keep cutting out.
yeah, my internet has not been great today. The second opinion consultation is $525 Canadian. And that's a little research prior to meeting with you, and the 1 hour on Zoom, and the written summary with the references, all the medical data that your doctor would need to explore those recommendations for you.
So that's all on Zoom.
Yes, that's right. Yeah, we were actually already virtual before the pandemic, but of course everybody's so much more familiar with Zoom consultations now. But yes, our consultations are all on Zoom, so you don't have to leave your home, you don't have to travel. And should we proceed with services for you, we have nursing services that come straight to your home. And then again, everything to do with the testing, we just need you to fill out a form, and we can take care of everything else for you.
So that will be $525 per person, I am assuming, right? There are two of us.
We could do both your case and your wife's case within that hour.
Yes, we've had sadly a number of couples who have had concurrent diagnoses of cancer, and I mean, we want to make it as easy as possible for both of you to get what you need.
Yes.
Absolutely, and be around as long as possible for each other.
Okay, so okay, sounds attractive, definitely. What about, if I may, I doubt that you're gonna tell me anything bad, but we already have some treatments going on with IV and stuff like that, but those are just general treatments, you know what I mean? It's nothing like a particularly for my type of cancer or my wife.
You mean a naturopathic treatment?
Yes.
Yeah.
Dr. Lemo from Vancouver is our secondary.
Yeah. So you're taking an integrative approach to your care.
Yeah. Well,
yeah.
You know, I've read some literature about things like a alkaline state of body and stuff like that. But you know, it's like right now we don't have any. You know, it's done deal, right? I have a cancer. Bella, my wife, has cancer. Is obvious. So it's hard to prevent cancer, which already exists, right?
Yeah.
Well, there are lots of things that you can do. Again, genetics is so powerful, and I feel like I'm sounding a bit like a broken record, but what we now know, and there are some excellent peer-reviewed studies that indicate that people with certain genetics will benefit from certain supplements, or should never take certain supplements.
Okay.
Some folks benefit from hyperthermia, other people no. Same with ozone therapy, mistletoe therapy, various other things. Depending on your genetics, those things could be beneficial, and with other types of genetics, they can make the cancer grow faster or just do nothing for you. So we definitely look into that once we have your genetics. We also, years ago, Alex began compiling a cancer-fighting diet based on nutraceuticals. This is kind of before nutraceuticals were really a thing or known. Really, like this is quite a few years ago. Now, you know, your naturopathic doctor has almost certainly recommended certain supplements for you to be taking. Again, based on your genetics, we may
Yeah.
make alternative recommendations to that. And of course, while you're on treatment and not, it may be better or worse for you to be on certain things. But there is some very solid evidence right now for certain supplements having a very powerful impact on slowing the growth of cancer and even reversing the growth of cancer with certain mutations. So there's a lot of value that you get from that information.
I agree with you because we are doing that. You know, the last year when my wife got diagnosed with that stage 4, surprisingly, almost no symptoms, neuroendocrine tumor. The first thing we have done it, we went on total diet, almost totally vegan, right? We removed meat from our diet completely, and sugar too, right? But that's total confusion for us, you know, created by too many informations. Everybody got their own opinion and so forth. It's very hard. I mean, okay, I see nothing wrong to be vegetarian basically, and I like it in many ways, and I think it does helps because you probably are aware of Dr. Warburg, right, who got 100 years ago a Nobel Prize for discovering that alkaline body is harder for cancer to thrive. And I'm not going to waste your time with that.
No. Yeah.
But I'm sure you probably are aware of that.
Yeah.
So that's the base what we are doing right now. You know, we're trying to, like with baking soda and so forth, and reduce intake of sugar, which apparently is also one of the harboring things for a cancer. Although sugar is everywhere, right? It's very hard to say. Very hard to.
Yeah, even in things that you wouldn't like. Why does sugar need to be in this? I don't know, but yeah, there it is. So you guys, Alex, do you want to say anything? And
yeah, well, you know, I think a lot of these things are not necessarily science-based approaches. There, you know, there can be some preclinical generalized data, but you know what we do is medical science. It's very different, and
I understand.
We try to stick with FDA-approved drugs and you know the basics of medical science rather than you know that sort of approach, which is more general. I mean, you know, naturopaths tend to give the same things to everyone, regardless of the type of cancer they have. It's just what they do. And some of those things, you know, there's studies that show that vitamin C can cause some cancers to grow faster and other cancers to grow slower. And then other people, it just doesn't do anything. I mean, that's true for most of these. If you don't know what the genetics, the molecular features of what you're dealing with, then you're just guessing. So by all means, a Mediterranean diet is very important. You want to replace meat with fish, cold water fish. And this is beneficial against cancers, heart disease, strokes, many different diseases. So, you know, there's a healthy approach that includes exercise and a Mediterranean-based diet, olive oil, lots of fresh fruits, vegetables, berries, you know, seeds and nuts. And yes, you want to reduce your meat. Doesn't mean you should not have any meat. You just want to reduce it significantly and replace it with fish.
Okay, thank you for
that. When we meet with you and Bella, we'll give you a copy of the diet plan that Alex has created, and all the references that are attached to that for the science behind those recommendations, and then you can mix and match with what you're already doing. It sounds like you two have made a really good start. You've made some big changes and you're working hard to help keep cancer at bay, and that's excellent. We just want to make sure that those efforts are paying off as much as they can.
Thank you. The thing is, you know, that I doubt that we eat so bad food even before we discovered that, you know, we have that problem. Definitely meat was more frequently on our table. Now it's hardly ever. If we do eat fish, it's usually salmon for a probably obvious reason. They got that omega-3 oil and so forth. And I don't know, but you know, yeah, in my opinion, that's far we can go. Now we definitely need the DNA test
Yes,
to get more accurate information
I
about
agree.
our situation.
Yes, 100%.
It just gives you so much more confidence in even these things you're asking right now. And you see the self-advocacy program I was talking about earlier, we teach you how to do your own research so that you can, once you find out what genes are driving your cancer, we can show you where to look to find out, okay, is this supplement a good idea for me? It might be great for you, but not for Bella, or the other way around.
Yes.
Or certain foods
Yeah.
might be so
You-
much more important for her and less for you.
You know, I'm happy in a way that I actually managed finally to get in touch with you, because these informations are hardly available. I mean, you can talk with any oncologist, they just don't
Talk about it.
talk about it.
Well,
Well,
they're not trained in that. They've got enough on their plates.
There's
Yeah, yeah.
that. They're not trained in it. They are super duper busy. They're also not really permitted to talk with you about things that they can't provide for you.
That's the most probable, not permitted to talk
Yeah.
to us about things, and then they probably try to cover their back too, because if they give me a wrong information, they think I'm gonna go now, whatever, sue them or something. I just want to get out, if it's possible, of that situation. That's all I really wish.
Yeah.
Right?
So
I don't
that's
think-
where, again, that's where, you know, that's really why we started this service, you know, over 10 years ago now, almost 12 years ago now. Because of our own experiences with loved ones with cancer and just the challenges we had, not certainly the medical oncologists weren't recommending genetic testing or targeted therapy back then either, but even once we found the information, just getting them to look at it and be willing to prescribe it was so stressful, really, knowing there were these options, but we couldn't get them. So as we started to get a little more savvy in getting them for people we cared about, it became obvious that this was something that a lot of people were dealing with. Yeah, so that's why we're here, is just to give you as much information as is possible about what's driving your cancer, and what is going to be best for you, whether in, you know, diet and lifestyle choices and treatment options. And because the concept of genetic testing is getting more and more known, and there is respect in medical oncologists for the value of genetic data, they can use that information to inform their treatment.
Yeah, I did approach the two doctors with that, two oncologists with that genetic testing, especially for my wife, you know, because stage 4 cancer is very serious issue. And I mean, she's healthy, and she sits next to me right now and doing kitchen stuff. And
Hi, Bella.
Hi.
Nice to meet you.
Hi.
the most
What
of
did
the
they
people,
say when you asked them?
they said nothing, right? Basically, they seems like I would be surprised that they know nothing about it. That would be shocker, right? They are simply not allowed, or whatever reason. I'm
But
not criticizing.
did they say we can't, or she doesn't need it, or what did they say?
I
What was
don't
their
even
reason?
remember, but I was
Okay.
simply ignored. Let's put that way. Just that question passed by with no answer.
I see. Yeah. Yeah.
Even though I just wanted to know, is BC Cancer does provide that service or that test, whatever you call, or is not? And as you explained to me, it seems like it's on us.
Within your consult, but I think we need to get on with another. We have some other questions right now, Michelle.
Okay.
Yeah.
Yeah.
Okay.
Do we have another question?
Do we?
Well,
Oh.
I mean, okay. My question is regarding that
Hernandez.
appointment.
Yes.
How are we gonna deal with that?
I'll put my email in the chat here, Ivo, and you can send me an email right away, and we will get you guys, we will send you the forms.
Okay, so you're gonna send me an email.
You can have a look at them before they meet with you. So there's my email in the chat there for you if you want to take a photo or copy that down. It's also, if you've downloaded the PDF that I loaded into the chat, everyone, please make sure you do that. Videos that we shared with you. Oh,
Okay.
I know. My computer has said, you've had enough internet for today, Michelle, I guess.
I think mine's cutting out too.
Do download the PDF that's in the chat before the meeting ends, because then it will disappear, but it will be emailed to you.
Okay, I lost you again.
Oh, you can email me, Ivo, directly, and we'll arrange this for you.
Okay, we can. Okay, after that video chat, we'll get in touch with.
Sounds good.
via
Yeah,
email.
I mean, we will help your doctor help you. That's our job.
Okay, what I'm saying is we can continue communication via email.
Yep.
After today's section, right?
Yes, absolutely, 100%. And we'll get you booked in as quickly as possible so both of you can get some information.
Okay, that sounds good. And
yes.
Okay, so
okay, I want to thank you for all your questions, Ivo. That I really appreciate. I appreciate you being willing to share about what's going on for the two of you right now. And the questions you asked are very, very important questions and very common questions. And I appreciate having an opportunity to answer them for you and just educate people about what's possible and how to get it.
So I appreciate too your, I mean, you know, that show, I mean, that I call it show, you know.
Yeah, the webinar.
My English is not that perfect, so I'm, for a lack of a better word, I call that show, right? But yes. It's just great to start from somewhere, right, and get some better knowledge about all these things, right?
Yeah, we say and have said since we began, knowledge is power, and there's a level of peace that you can start to have when you understand better what there are options, or steps I can take, or things that I can do to have more control over what's happening. It's such an important thing for you to be experiencing.
Well, this kind of hope.
Yes, hope. Yes.
This is what is all about, right? To think about how to get out of this situation, if it's ever possible, right? But at least there is something that you can reliably go on, right?
There is something for human beings naturally, even when we know that the outcome isn't ideal, when we know we've done our best, there's a different level of peace and satisfaction that experience. And we don't want to, especially with life-threatening things, we do not want to be wondering. We don't want to be wondering, could we have done more? Was there more we could have done? Did we get the best? We want to know, and we want to be on it as quickly as possible. And that's what we're here to help you do, for sure.
We lost Alex.
I did, I know. Does anybody else have any questions before we wrap up? We are at our time for today. If you do, you can post them through the chat. I'll sit around for a moment or two. We will be having a part 2 to this webinar, and you'll get an email to let you know when that's happening if you'd like to come, or just you can sign up and get the replay, whatever is easiest for you in your life. Where we'll talk a little bit more about different targeted therapies. But that information is really most beneficial once you know what mutations you have, because then it's, oh, yes, that one.
He has to start there. He has to start with DNA. I agree with that.
Yeah, that's right. There's a few different types of tests, but we'll talk with you all about those when we get a chance to meet with you. And anyone else that was here today, obviously you've just heard all the different ways that you can access information from us, whether our course and a consultation with Alex and various other things that we can help you with. So If anything that you heard today is of interest and you'd like to find out more, let us know. The PDF and the PowerPoint will be sent to you in a copy of this presentation as well. And you are welcome to share this with anybody, other folks that have similar types of cancers that you know, and with your doctor. Our goal is to make sure everybody is as well educated and that these things become part of standard care as quickly as possible, as they should be. So thank you very much for joining us.
Thank you, Michelle.
Thank you. We'll see you soon.
Thank you.
Take care.
Thank you,
Yeah.
Alex and Michelle.
Thank you,
much.
Alex.
Bye.
This information make us stronger.
Great. I'm glad, Bella. Thank you.
Thank
That's
you.
good to hear. Made
Yeah.
my day. Take care.
Bye-bye.
See you
Have a
next
nice
time.
day.
Yeah.